Awesome. All right. Thank you everybody for joining. I hope you're having a great morning. I certainly am, and I'm happy to be here. So going to jump right in today, but first, let's start with some housekeeping. If you got any questions, type them in the Q&A section. I'll try to get to them all at the end. Likely I will have time to answer every question. And my name is Matt Walker. Today we're going to talk about AC and DC coupling of a PV system with SimpliPhi batteries. Note that this presentation is NAPCEP accredited, so if you need CEUs, just shoot me an email. I'll have my email at the end. Awesome. And then last but not least, I can't unmute you, but like I said, we'll have time for plenty of questions at the end. Cool. So let's start out with an overview of our company and a timeline really of our growth throughout the past decade. So we were founded in 2010 as OES Energy. When we had already, our founders had already had several successful deployments in the film industry, kind of proving our roots in the mobile applications there. And we were really founded to provide a solution for what was a major issue on the market and really still is today, is unsafe and toxic lithium chemistries. So there were, of course, and still are lots of thermal runaway events and fires with these different lithium chemistries. And we found that lithium iron phosphate chemistry was more robust and much safer, yet it didn't sacrifice any performance. So we began using that in our batteries and power packs. And then in 2011, when the military came knocking, asking for proposals for a project, they really didn't even want lithium batteries for this project. Yet we proved them that lithium iron phosphate would be much safer, would not have the same concerns of fire, and yet would not have any of the limitations of lead acid batteries. So after rigorous testing at a couple of their facilities, one including Aberdeen Proving Grounds, which is not too far from my hometown in Maryland, the military did decide to go with our solution. And that's how we began military sector deployments, as well as residential and emergency response. So in 2013 and 14, moving forward, we began developing more customer-centric and installer-centric solutions. As you can see, this battery bank on wheels here, we still have something similar. And then in 2015 and 16, we relaunched as SimpliPhi Power, still diversifying our product line, and now we are ramping up manufacturing at our Ventura County facility and still adding more and more solutions, really focusing on the customers and installers using our products. So all our products are actually manufactured in Ventura County, like I said. We have chosen, as I mentioned, lithium iron phosphate chemistry, but also when we touch on form factors, pouch cells are a little bit more prone to puncture or swelling. Prismatic cells, they're great, but just a bit bulky. And cylindrical cells have built-in short circuit protection. Additionally, they have the longest lifespan and all around just the best performance, making them a clear choice for a battery. So those lithium iron phosphate cylindrical cells are the building block of our batteries. As I mentioned, we were founded to solve a problem, which was unsafe lithium chemistries. However, now there's an evolving problem in the market, which is the limited access to safe, reliable, and affordable and sustainable power. So this is really caused by a few things, of course, but the main will be escalating energy costs and failing infrastructure. So of course, in the US, if you're living here, you've seen the price per kilowatt hour slowly rise over the past 10 years, and that's not going to stop rising. Additionally, there's our grid is really just not designed for distributed assets. Causes a lot of issues with the equipment. So with the addition of all these electric vehicles and battery banks and solar power systems, there's been a whole bunch of issues, and what we want to provide customers is a solution with distributed assets. So allowing the customer to take back the control of their power. Literally taking power over your power. You'll have to excuse my pun on that one. So decarbonization is becoming demanded now by cities and utilities alike, and unfortunately they just often don't have a clear plan to meet those goals. So that is why we're here to solve those problems. Our batteries can be used in a variety of applications, from peak shaving to time of use rates. So often you'll be charged a demand cost if you're ever pulling more than a certain amount of power. And you can use battery storage to meet that excess power demand, even if you don't have PV. You can just buy power when your demand is low and then use it when your demand is high. You can also use batteries to combat time of use rates. So being charged a slightly lower rate at noon, you may want to buy, or sorry, early in the morning, you might want to buy your power when it's cheap, and you might want to use it when the power is expensive. So when you're getting charged extra, you just use the battery power that you already have purchased at a cheaper rate. And you can do this with or without battery, with or without solar PV. All of our solutions are not only up to, held to the highest safety standards, but also usually certified to the highest and newest safety standards as well. We want to make sure that you can use our products regardless of your authority having jurisdictions requirements and whatever code they have adopted. Therefore, we're always on the leading edge of getting our products UL certified. So some UL certifications that are applicable here are 1642, 1973, and 9540. Those are cell, module, and system level certifications. And 9540A is becoming increasingly important now. That is a test protocol, not a certification. Additionally, these really are needed for just about every system nowadays. If you think that your system is ever going to be inspected, then it's needed. And even if your system isn't going to be inspected, it's still recommended. For example, for insurance purposes, or if you were to ever sell your property. And I don't want to go too deep into the standards, but we did recently have a safety and standards training that's on our YouTube channel now if you have more questions about that. So to give an overview of what we're going to talk about today, we're going to discuss AC and DC coupling, what those terms mean, what are the layouts of each system type, what are the advantages of each system type, and even what are the limitations. And then finally, we're going to briefly touch on some products that we offer that meet the needs of either or solution, as well as going to briefly touch on our IQ program at the end as well, because I know we've got a lot of installers here today. And man, we've been getting a ton of photos of just some beautiful installs. So I'd love to highlight some more of you guys. So jumping in here, basic definitions of AC and DC coupling. AC coupling means that AC power is coming off the roof and then converted to DC power to charge the batteries. DC coupling means that the PV array is coming all the way down to the batteries and into the batteries still as DC power. So really, coupling just refers to how the solar panels are connected to the battery relative to charging. First, let's talk about DC coupling. DC coupling is when you have DC power generation all the way from the power source down to the batteries. This means you're going to be using some type of charge controller. The charge controller is going to not only make sure that the PV panel is producing as much as possible, but is also going to charge the battery according to how you've programmed it. So it will meet certain voltage and current specifications given to you by us or other battery manufacturers. You do have some PV arrangement considerations when you're using a charge controller. For example, the size of the string. If you've got a 150 volt charge controller, then you can really only put 3, maybe 4 panels in series most times. Additionally, when it gets cold, the VOC tends to fall, so you really don't want to be, if you've got 150 VOC max on your charge controller, you don't want your panels to be at 149 VOC, because then on a cold morning, they could go slightly above and potentially damage your charge controller. Shading is something to think about when you're laying out your PV array. And if you want, you can use DC optimizers to mitigate that, but often you just want to place your array so that you don't have to worry about it. Now there's also charge controllers that have 600 volt inputs, now that I'm thinking of it, and those are, of course, more convenient for larger strings. However, you're still going to be supplying AC power to your loads through the inverter. So regardless of how the power is produced, AC or DC coupled, when you're powering your loads, it still at some point needs to be converted to AC power. So let's talk about charge controllers. What does a charge controller do? This is going to regulate the voltage and the current going into the battery bank. And of course, it's going to also make sure that the power source, whether it be PV, wind, or hydro, are producing as much as they can. So there's 2 ways that the charge controller can ensure that the power source is producing as much as it can. One way is MPPT tracking. It's going to, maximum power point tracking, shortened to MPPT. An MPPT charge controller is going to, let's say it's at 25 volts for the array, it's going to bump up to 25.1 and say, are you producing more power? And if not, it's going to bump down to 24.9 and see if there's any more power coming out. And then just go back and forth to always find the maximum power point voltage. It's going to be constantly doing that. And then to charge the batteries, of course, it's going to be doing exactly what you've programmed it to do, whether you've programmed it to output 56 volts or for a 24 volt system, 28 volts, etc. Now, a PWM charge controller, that's a bit different. Pulse width modulation, and with WIDTH. So what it's going to do is turn on for a certain amount of time at a certain voltage and then turn off, and turn on for a certain amount of time and turn off again. So by shortening or lengthening the length of time that it's on, they can modify the width of the pulse, and that's going to affect the voltage that your battery effectively sees. This is going to be slightly less efficient for a PWM charge controller, just in general, and I definitely prefer MPPT controllers. And now we see most controllers being produced as MPPT, but some PWM controllers are still around and they still work great. There's no issue with them. So this is just a brief layout of a DC coupled system. Now, one thing I want to point out is these Tigo TS4Fs. These are the rapid shutdown only PV modules. And you can also use the TS4Os here, the optimizers, to mitigate any shading concerns. It's basically an MPPT for each panel. Not exactly, but that's essentially how it works. It's going to make sure that if one panel is shaded, that the other two panels can still produce optimally. Those are all going to be run through a wire that runs through this Tigo transmitter, and the Solarc has a 12-volt power supply that keeps that transmitter on. If the Solarc ever shuts off, the transmitter will shut off and then turn off each PV module. So this is going to be able to meet your rapid shutdown needs, most likely. Depends on your jurisdiction. We'll talk about that a bit more later. These are our boss cabinets, great for outdoors. Really, this whole system can be put outdoors because the Solarc is offered in an outdoor rated version. And I have one more diagram I want to brush over as well. I really like this diagram specifically just because it has this very clear DC bus bar. So what I want to point out here is the solar panel goes through the MPPT, and the MPPT charge controller is going to land on this DC bus. And additionally, the inverter pulls power from this DC bus as well, where the batteries are landed. So a lot of people think that an AC coupled system can be better because you can bypass your batteries and send your PV production straight to your loads or the grid while it's being produced if you're using it. But really, it's no different here. If you are producing power and your batteries are full, it's not going to charge the batteries and then come back out. It's just going to hit that DC bus and go right to the inverter or to loads or a grid. So AC coupling, let's do an overview of that. AC coupling differs from DC coupling because the PV modules are producing DC power, but if you have microinverters, they're immediately converting that power to AC power. So you can accomplish AC coupling two ways. You can either use a microinverter on each PV module, or you can use a string inverter for a string of PV modules in series. Now, either way, after this microinverter or string inverter, you're going to need a battery-based inverter to convert the AC power to DC power. There's a little less considerations here to be made based on PV arrangement, and ultimately the microinverters are going to mitigate a lot of those shading concerns similar to an optimizer would. A string inverter, not so much. However, if you've got shading on one panel on a string of 5 panels in series, it's going to kill the production pretty drastically. Oh, excuse me. And then another thing to point out here is that AC coupling and DC coupling alike, they're still supplying AC power to the loads from the inverter. So another misconception here is a lot of people think that AC coupling is more efficient because the panels produce AC power. It's not really the case because to power loads or send power to the grid, it's, the power has to go through one conversion from DC power to AC power at some point, somewhere along the line, regardless of if you're AC or DC coupling. So the battery-based inverter has a built-in charger to charge the battery. So it's similar to a charge controller, but it's going to use AC power. But it is going to still be able to meet those exact set points, like voltage and current that you've put in. And using a generator is essentially the same as AC coupling because you have an AC power source coming in, going to the inverter is going to convert that AC power to DC power, or just send that AC power directly to the loads from the generator if you're using it. Frequency shifting, good topic to touch on here because a lot of people don't realize if you just have a grid-tied PV array and no batteries, when the grid goes out, your PV is not producing at all. It's also down with the grid. However, if you do have batteries, you may have the ability to use frequency shifting to keep your AC coupled PV array producing power. So how this works is the battery-based inverter is going to notice that the grid is down. It's going to use the automatic transfer switch to disconnect from the grid so that there's no safety concerns for the line workers. Once it's disconnected from the grid, it's going to produce it's going to basically mimic the grid. It's going to produce that same voltage and frequency that the grid was previously producing, which will turn the microinverters back on as they see that grid signal. Now, if your batteries then become full and the grid is out and you can't export that excess PV power to the grid, what the battery-based inverter does is it shifts its frequency. So if it's at, let's say it's at 60 hertz and it goes to 60.5 hertz, for example, those microinverters are going to see that frequency shift and they're going to reduce the power that they're pushing out so that your batteries don't get overcharged. Now, this is a good point to note, the C/2 rule of our batteries. You really don't want to have an AC coupled PV array more than twice the kilowatt output of the kilowatt hour capacity of the batteries. So if you've got a 10 kilowatt hour battery bank, half. So if you've got a 10 kilowatt hour battery bank, the most PV you want is 5 kilowatts. The reason for that is when the grid goes down, your PV takes a second to shut off essentially, and it's going to continue producing power for a few moments. If those batteries are already full, it can cause a high voltage event and overcharge the batteries. So that's why we want to make sure that, we're using half the amount of PV per kilowatt hour capacity of batteries. So back to frequency shifting real quick. If you're not sure if your AC coupled project is going to have frequency shifting, you should do two things. You should call first the battery-based manufacturer, but more importantly, the grid-tied inverter manufacturer. They're going to know if their inverters have the frequency shifting capability. So here's an example of just a grid-tied PV array. There's no batteries here, so when the grid goes down, your PV array also stops producing. Now look how easy it is to just drop in this Schneider XW Pro and Boss cabinets full of batteries. This is an easy retrofit for a grid-tied PV system to make it a battery-based AC coupled system. Additionally, an advantage here is you can also get our access unit, which has the Schneider inverter, the XW Pro, inside of it already, as well as some batteries inside of the cabinet. This is all outdoor rated. That way, all your equipment can be outdoors, which all this stuff, the array, microinverters, sub panel, and main panel, that's already outside. So being able to put all your additional equipment outside might be really nice. You might want to check out that access unit. We'll talk about that a bit more as well. Cool, so we've kind of gone through the overview of AC and DC coupling. Let's talk about some applications. Some applications for DC coupling. First and foremost, off-grid. If you're off-grid, you basically always want DC coupled. AC coupled off-grid just doesn't make a whole lot of sense unless it's a massive system. Additionally, DC coupled makes a lot of sense for a battery backup system where you're just using this battery system for, you want to keep it full, sell the excess to the grid, but keep it there for when you have a power outage. Island mode, it's nice because additionally, when the grid goes down, this is a seamless transition to your PVs already being able to either continue producing or stop producing, whether the batteries are full. It's independent of the grid being on or off, right? So there's no AC connection between the panels and the batteries. That's why this makes a lot of sense. Additionally, if you need features like time of use selling, not selling, just time of use, or peak load shaving, DC coupled makes a lot of sense for that because it's difficult to have more granular control over where your power is going when you have an AC coupled system. It's just the AC power is just directly connected to the grid pretty much all the time, unless you choose to shut the grid off at a certain time. For large scale commercial and industrial, you may use a massive DC to DC converter. This is basically a giant charge controller, or a larger MPPT like that 600 volt charge controller we talked about. I think Schneider has one right now. There are some PV considerations. I kind of mentioned these before, so I won't talk about them too much again. I don't want to bore you guys, but it can be pretty easy to install a DC coupled system. Sometimes an AC coupled system is easier. It really just depends on the project. But if you're retrofitting an existing array that's already grid tied, DC coupled probably doesn't make a whole lot of sense. That's where you'd want AC coupled if you're retrofitting an existing array, or if you have a giant off-grid system or giant battery backup system. This is a little bit more limiting, as I mentioned, for the TOU and self-consumption, because you don't have as much control when you're producing AC power. So if you do not want that power to be exported to grid, if you instead want to use it yourself, you really have to just shut the grid off during those certain hours. Just disconnect from the grid during the day, for example. Same with peak shaving. This is a little bit harder to do, if at all possible, with AC coupling. It's going to be much easier to do with DC coupling. I've kind of touched on most of this stuff already, but just to recap, there are, challenges when you're retrofitting an existing PV array and it's already grid tied. You would have to rewire most likely the entire array to turn that into a DC coupled system. So it just doesn't make a whole lot of sense. In that scenario, just leave it there as AC coupled. The differences we talked about between AC and DC coupled when the grid goes down, if you have an AC coupled array, you need to make sure you've got frequency shifting or your array won't be producing. If you've got a DC coupled system, your array is not even going to notice if the power goes out. So it's a much more seamless transition. So in my mind, there are usually more advantages to DC coupled. Does still depend on the application, though, of course. So one of the misconceptions of a DC coupled system, this is something we didn't really touch on. A lot of people used to think that DC coupled systems could not be grid tied at all. They couldn't sell to the grid, and it was really just for off-grid systems. This is not the case, and this was just derived from the fact that it's so difficult to retrofit an existing PV array that's grid tied to become DC coupled. There are some efficiency differences as well. So using DC optimizers on each panel versus grid-tied inverters, those are going to be very similar in efficiency. However, if you're converting power from DC on the panels to AC on the microinverter, back to DC in the batteries, and then back to AC to power loads, that's definitely less efficient if you can skip that DC to AC conversion in the middle and just have panels DC to battery DC and then AC to loads. So it's much more efficient generally to use DC coupled, but we're talking about a couple percent. I probably shouldn't use the word much more efficient, but it is slightly more efficient most times to use DC coupled systems. Now, how about rapid shutdown? How does that play in here? This is always evolving and changing, so here's my disclaimer. Don't listen to what I have to say as the final word of advice. Make sure that you check with your local jurisdiction. Oftentimes for DC coupled though, you can get away with just a shutoff box for the ground mount. But if you need module level shutdown, there is options like some of the DC optimizers have this built in, or there's rapid shutdown only PV attachments from Tigo. If you need battery level shutdown, you want to disconnect your batteries from the system, that's where a remote trip breaker might come in handy. If the remote trip breaker isn't an option or your jurisdiction doesn't like that, you can use the single button shutdown on the SolArc. So the SolArc has the ability to disconnect the inverter, PV array, and batteries all in one button. We'll discuss that a little bit more too. But that same solution works for AC coupled SolArc single button shutdown. Here, the microinverters are basically always going to meet your rapid shutdown compliance needs for the panels. Now let's just jump into some examples here. For DC coupled, this is the example I used earlier, except I've added the red button. Basically, the SolArc, when you press this normally closed button, it opens the connection, and I believe it's normally closed. Perhaps it's normally open. I will need to check after this. But when you push this button, basically it's going to tell the inverter to shut down. The inverter is going to stop powering this transmitter, which is going to send a signal to these Tigo modules to shut down each PV module as well. It's also going to disconnect from the grid when you press this button, and it's going to disconnect the batteries from the inverter. For an AC coupled system example, this might not work for all jurisdictions, as some of them are a little bit past this, but for many of them, you can just get away with just a clearly labeled PV shutoff box. And this is going to go somewhere close to your sub panel, but this is, again, the same system I used earlier. And as I pointed out, I want to point this out one more time, is that the access unit would be great here because it can all go outdoors. So the access unit's basically going to condense these all into one unit. These batteries and the inverter all into one unit right here. Cool. A few more system design considerations with DC coupled. With DC coupled, often you're powering a critical loads panel, and know that you powering that critical loads panel with the inverter, you got to do some sizing calculations there. Make sure that you're not pulling too much power from the inverter. You're going to be limiting the amps through the charge controller. This is nice because if you have too large of a PV array, you can still kind of tone that down through the charge controller. So the C/2 rule for PV arrays coupling to batteries, that really only applies for AC coupled, because you can always limit the current effectively through the charge controller. Now, some inverters have that feature, but I personally wouldn't really trust it. It's just a very new thing, and I don't want to see your battery bank get damaged. One consideration, again, with DC coupled is that you often need to use smaller strings, and some people realize that they're going to need to have 6 strings of PV, and they think that's going to be a pain. But honestly, with a combiner box, it's not that bad. But gotta consider your wiring runs. If you've got DC power coming off the roof at 150 volts, you don't want that to drop 10 volts by the time it sees your charge controller. Got to make sure you size the wires appropriately. There should be less than a 3% drop in voltage across the wires. Blue Sea Systems has a great calculator on that to help you size your wires. So if you need help with that, I'm happy to point you to that calculator. As I mentioned, a lot of these newer inverters have this feature to limit amps through the inverter charger, but I personally just don't really trust that. And I think it's still really important to size your PV array correctly, especially for that moment when the grid disconnects and the array is still producing. And we talked about frequency shifting. This is becoming really essential unless you want your PV array to stop producing when the grid goes down. One advantage to AC coupling is many times it is a little bit easier to figure out the wiring. There's less wiring and you can have larger strings. Since each panel, if you're using a microinverter, essentially has its own optimizer built in, and won't be you won't be limiting the current of other panels in series as long as each one has a microinverter. For commercial and industrial, again, these massive DC to DC charge controllers, they are out there. I don't work with them much, so I don't have too much to say there. But the rapid shutdown requirements are, of course, going to change for giant commercial and industrial systems. For AC coupled, this is often the way to go with massive, utility scale systems. It's just how it's going to be. It makes things much easier and often more efficient when these massive systems are AC coupled. So let's do a quick overview of some PHI products that we have that meet the needs of these applications. Excuse me, my mouse is frozen. There we go. Awesome. So PHI batteries. This is our standard battery, our bread and butter, our 3.8 kilowatt hour building block for any size system, any power and energy needs that you have. This can take care of it. It's got the ability to be AC or DC coupled. Really, the battery doesn't care. It's not going to know. You're just pushing and pulling power to it. In either case, you're going to need a battery-based inverter, though. And as I mentioned, DC coupling can be more efficient in most cases. If you're not using the power right away, then it skips one of those conversions from DC to AC. For AC coupling, typically 48 volts is recommended, and I really don't see a lot of AC coupling battery-based inverters able to accept 24-volt input. Our access, I mentioned this is great for an AC coupled system, especially because it can all be put outside, right? It's the inverter is inside of here and the batteries are inside of here, all one unit, and all your other equipment's already outside. So it makes sense to put your inverter and batteries outside as well. This comes with Schneider or Solarc inverters, and both have the option to AC or DC couple. If you want the Schneider, it will, you'll have to add that 600-volt charge controller, and it's got an MPPT. If you want the Solarc inverter comes automatically with 2 MPPTs built in. Both of the inverters have AC coupling ability, and they are generally compatible with all of the newest grid-tied inverters. Again, still check. If you have any questions, if it's compatible, you can call us and we'll help you get in touch with Enphase or whatever microinverter you're using. Again, for AC coupled, make sure that your PV is limited to C/2 if you are AC coupling, and that you're able to meet your critical loads needs with just the inverter. Because in an outage, right, you're going to be pulling power from that critical loads panel. If you have some sort of a surge, the grid isn't going to be there to help you, but your battery-based system, batteries and inverter, are still going to try to power all those loads. So that's why it's important to size the critical loads panel properly. A main breaker in there is going to be really useful, a properly sized main breaker as well. Don't overload the critical loads panel. Oh, another point to make here is you can add additional storage to these access units with boss cabinets if you want it outdoors. So these have knockouts on the side of both the access units and the boss cabinets, and you can parallel additional battery storage if needed. Both options, the Schneider and the Solarc, they're going to come with the automatic transfer switch built in already, so you don't need an additional one. Yeah, I already touched on all the equipment being outside. For AC coupled, all the equipment, of course, is outside, but for DC coupled, that's sometimes the case as well. A little less likely, but it does happen. As far as the AC coupled PV limits I mentioned, I'm just going to make it crystal clear. These are the limits right here. For Schneider access units, the 3 battery version, you can couple 5.7 kilowatts of PV. The 4 battery version, 6.8 kilowatts of PV. And the Solarc 12K, 7.6 kilowatts of PV. Any questions about that, just reach out. Now, quickly, some tools on our website that will help you design the best system you can. First, make sure to check out our support line. This is under our support tab, we have all of our manuals, spec sheets, and integration guides. Now, I'm going to do a quick jump into our website and just show you guys where that is, but also you can reach our tech support and pre-sales line by phone. We really do pick up the phone. Sometimes it's me, sometimes it's one of our other associates, but we really do pick up the phone, or we'll call you right back or email you very quickly. And our pre-sales line is not just a bunch of salespeople. They also have extensive experience in the industry, and they're coming from an engineering background. So let's see if I can get this to work. Bear with me if it takes a while. This is our support tab, and then here is where you're going to find all the documentation you need to troubleshoot or install the batteries. Now, if you go to the sizing calculators, this is what I'm going to talk about in just a second here. Our quick 3.8 battery bank calculator. This is for designing, a system, of course, but it's really just taking into consideration your loads and the days of autonomy. So it's very simple. This is going to consider your inverter, your charge controller, the other equipment in the system to make sure that your battery not only meets the needs of your loads, but is also sized properly with the rest of the system. Our lead-acid battery bank calculator, of course, can help you replace an existing lead-acid battery bank by considering the specs of the current lead-acid batteries. and our LCOES calculator, levelized cost of energy storage. This is going to help you, especially if you're an installer, to help the homeowner understand why upfront cost is not the most important thing. The most important thing is the levelized cost, which is the cost per kilowatt hour that you're getting out of the battery. So this can help you compare the cost of different battery storage solutions. Awesome. These are the tools I just brushed over, so links are here. And last but not least, I want to first give a shout out and thanks to all our installers. You guys have been doing awesome work recently. Been seeing all these installs come in. Some of them are really beautiful and they've been really well designed. And want to point out that if you are a distributor, you should encourage your installers to get involved because it can help you increase sales from SimpliPhi products, right? If you've got a customer who, an installer who buys from you and is getting more and more installation calls, perfect, that's great for you. Help him get up on this map and get more exposure. It's just going to result in more sales. Additionally, it's going to show that you and your installers have increased knowledge of our products and that we're in touch with you. This goes a long way. As an installer, you're going to get the ability to highlight your projects. So if you want a installation featured, just send us over some photos and we'll see what we can do. We are featuring the new installers in our IQ newsletter, and those have been getting a ton of exposure. Additionally, this where to buy map is going to help customers find an installer near them, so we can add you there as well. If you're already installing our batteries, just apply. It takes about 2 minutes, and we'll see if we can get you through the program. And if not, we'll let you know what you need to do to get there. But it's real quick, so if you're already installing our batteries, go ahead and apply right here at this link. To kind of summarize what we've gone through today, this is my last slide. SimpliPhi is founded as a solution to unsafe lithium chemistries and the limitations of lead acid batteries. Lithium iron phosphate solves those problems. We've been around for a decade and we're solving the issue of limited access to affordable and sustainable power for people, communities, and businesses everywhere. That is our mission, and we're accelerating the transition to a clean energy grid. While doing all this, we want to deliver the most economic value we can to our customers and really just support you immensely through your transition to clean energy. Awesome. So thank you everybody for joining me. I'm going to jump into the Q&A now and see what questions you guys have for me. If you haven't put in your questions yet, feel free to shoot them in now. Excuse me, just reading. This is a long one. In an off-grid DC connected configuration, his charge controllers are calibrated to actual battery voltage measured at DC bus bars. The inverter battery monitor measures voltage about ½ volt higher. Does this voltage variance, incorrect at the inverter battery monitor, matter? Is the charge controller voltage reading used to manage battery bank charging levels? So yes, depends. I mean, what's your full system layout? You should contact our tech support team so that we can help you the best. I mean, want to try to keep this a little more general, but basically your charge controller, as long as that's calibrated correctly, that means the solar panels are going to be charging the battery bank correctly. However, if you're ever using a grid, to charge the batteries. The inverter also needs to be calibrated. Plus, if you ever get near, a low battery cutout, you want to make sure your inverter is calibrated for that as well. So yes, this does matter. Any voltage variance in any of your equipment is going to matter, and you should definitely calibrate it. So if you need help, give us a shout. Does the access unit have built-in heating options? Yes, the access unit can come with heating options built in. If you would like, you can get it with hot start heating pads. Those are really nice because they have a built-in thermostat. They come on when the batteries are in danger of getting too cold, and they turn off when the batteries are warm enough again. So I've seen them used in several feet of snow. Where is that wire sizing calculator? Oh man, I'm gonna have to dig that up for you guys. If you just Google Blue Sea Systems DC wire gauge chart, that is where you're gonna find it. And if you don't find it, just shoot me an email. I think my email is at the bottom of the screen here. Yeah, training@simpliphipower.com, and I'll make sure to send you a link. Hope you'll be sending out the presentation after the webinar together with the NABCEP cert. Again, just if you need NABCEP credits, shoot me an email. I'm not going to send them to everyone unless you ask, because there's so many of you here right now. That would take me all day. But I'd be happy to send you NABCEP credits if you just send me an email. And in a couple days, you will all get a copy of this presentation recording. The link will be sent to your email that you registered with. Is it safe to say it's wise to install AC coupled unless doing an off-grid setup? No, I would not say that. I would say generally, I personally would prefer DC coupled unless doing a retrofit of a grid tied array. So I think DC coupled is the way to go in most cases. Personally, really you can do either, but I think DC coupled has less limitations and is more efficient. And especially with DC coupled, I really like how when the grid shuts down, the DC side doesn't even notice, right? Like the PV array and the charge controller and batteries, they don't even barely notice that their grid is out. There's no real event that has to occur. The PV array can continue charging the batteries can continue powering the loads as if nothing has happened. So that's why I really prefer DC coupled. How well will LFP batteries perform at 0 degrees Fahrenheit? What do you mean by perform? Because the batteries are not going to lose a significant amount of capacity when it gets cold, but they shouldn't be charged below 0 degrees Fahrenheit, or below freezing, so 32 degrees Fahrenheit. If you're discharging the batteries or even just having them stored, make sure you keep them above -4 degrees Fahrenheit. So that's all on our spec sheet. Any other questions about that? Let me know. How can I get a shirt like yours? Actually, if you were to become a certified installer, I'm sure that I could make a request to get you a nice shirt like mine. So you should apply to become IQ certified. That's what you should do. What is the product availability and warranty? Availability depends on your distributor. We don't really sell direct, but we'd be happy to help you find a distributor with the soonest availability. Let us know what area you're in. Generally, though, it's much better than other companies, as since we do have this large distribution network with many different distributors, they all often keep our products just stocked. So that helps us get the product to you the fastest and the cheapest. Our warranty is a 10-year flat warranty on the Phi batteries, so they have an 80% end of life capacity remaining. at the end of the 10 years, and there's unlimited cycles and at any depth of discharge as well. So you want to set your low battery cutout to a minimum of 48 volts. And then that will make sure that the batteries don't get discharged too low. That's 0% state of charge for the warranty. circuitwizard.bluesea.com. That is the link for the Blue Sea wire gauge helper thing. So also there's a DC wire gauge chart that's found on Blue Sea's website. So check that out too. If you're not sure what inverter is compatible with your microinverters, call the microinverter company first. They have a good lay of the land there. What is your email address for NAPCEP certs? Right here at the bottom of the screen, training@SimpliPhiPower.com. Awesome. Thank you everybody for joining, and I hope you have an awesome rest of your day.